Welcome, everyone. Thank you for dialing in. Are we still in the COVID era? No, in person. So thank you for joining us in person. It's been a great reInvent so far. I hope you're having an enriching and inspiring experience. I'm Prateek Sharma. I'm a Principal Solutions Architect with AWS. I've had the excellent opportunity to work closely with Netflix for last 4 years. And I've had the opportunity to collaborate with various teams at Netflix and work on some really groundbreaking projects. Like many of you, I'm also an avid Netflix user. I'm in love with the content they give me. And whenever we log in, like there are over 240 million customers that Netflix have. When you log in, you get a very personalized home screen. Think about that, the enormity of the challenge here. 240 million or more customers, when they log in, they instantly get their data on the screen. And not only that, I'm also marveling the resiliency that Netflix has. It has never gone down for me. Whenever I open it on my phone or my TV, it's always there, ready to entertain us. And think about the challenges that are behind the scenes of bringing that kind of experience. It's a testament to the robustness of AWS foundations and strong innovations at Netflix that have built so many resilient architectures. Now, when you open the home screen, there are hundreds of microservices that get called out, and all of these microservices need some data to quickly display the content that you're so eager to watch. And the enormity of the scale here is just mind-boggling. Not only that, they also have to factor in how to fail over. So if something goes down and you have to fail over to another region, you need to make sure that the data is also present in the other region. And at the scale of Netflix, if each developer team is given the responsibility to maintain this level of resiliency and rapid data access, it's going to be an overwhelming challenge for all these teams. This is where Prithviraj, Sriram, and the team come in. They have dedicated many years of their life in building out a system called EV Cache that enables this rapid data access and multi-region replication seamlessly for developers, where they don't have to worry about any of the challenges. They just need to focus on the business use case they have and push out the application code. So we are in luck today with Sriram and Prithviraj, who are going to dive deep into EV Cache and walk us through their journey. So welcome, please.
Thank you, guys. So how many of you use Netflix here? Okay, I still see some hands down, so I'm going to give you guys 30 seconds to hop onto the internet and subscribe to the service. It's awesome. Please use Netflix. All right. So today the topic is going to be how Netflix essentially does global replication of its caching engines. And when we talk about Netflix is really powered by hundreds and hundreds of microservices. So a 1-hour talk will never be able to do a justification on doing a deep dive on all these microservices. So the focus of this talk is going to be on caching. And I was here along with my another colleague in 2021 reInvent doing a deep dive on the caching layer. But today we are not going to talk so much about caching, but we are going to focus more on how we essentially take the caching engine or caching layer that is present in one region and replicate the data to multiple regions, and how we have done it. So this is Mary Kondo. She's a very famous Japanese author and also a TV show host. And the philosophy that she sort of tells to her audience is hold on to things that really spark joy and discard everything in your personal space. Netflix has a similar mission, which is to entertain the world and really spark joy through content to its members. And what you see is primarily the shows and movies. But when you imagine a world where you had a tiring day at work, you came back home, you are relaxing on your couch, you clicked your favorite Netflix show, and it took a minute to load. Frustrating, right? Luckily, that's not the world we live in. We have a far better experience where once you log on, once you click a title, it renders the content fairly instantaneously for you, regardless of where you're trying to stream it from. Thanks to the unsung heroes of Netflix engineering and definitely AWS for making that happen. let's get into the agenda itself. So we're going to spend a quick few minutes giving you the introduction of the caching engine that we're going to talk about. Why do we need to do a caching data, right? It feels very anti-pattern. Like replicating a database seems okay, but why do you want to replicate a cached data? So we'll get into the nuts and bolts of why we need to even do that. And then we talk about the design and architecture of the system. And we are going to take you through a window of how we manage a system like this. Like it's a pretty high-scale system which does close to 30 million RPS per second. And we are going to touch upon efficiency improvement. So 2023 is the year of efficiency, as the Mark Zuckerberg has alluded. So I'm pretty sure all of your, so have you guys invested in any efficiency efforts in 2023 to reduce cloud spend? Great. So that's Netflix as well, and we are going to talk you through how or like what kind of investments that went into making this a lot more cost effective. And finally, we are going to also give you a sneak peek into what happens in our lives as an engineer. It might be interesting for a lot of you, so we'll spend some time on that as well. And then we are going to leave you with some of the future items that the team is looking into. All right, so this must be a pretty familiar site to you. Once you hop onto Netflix, once you click on your profile, you get a personalized view of your own homepage. And like, let's say you are sharing your account and you wanted to peek what that other person is looking into it, you would have probably noticed that their homepage looks completely different than yours. And part of the reason is there is a ton of personalization algorithms and ML algorithms that are involved to make sure that whatever you see is something that is going that you're going to click and watch it. So it is highly curated, highly personalized for a particular profile or a particular member. Now, what you're seeing here is a fancy call graph, right? Essentially, this call graph corresponds to all the microservices that get invoked. I wish I could zoom in, but let me just elaborate what these are. The leaf nodes that you're seeing are essentially either the database or the caching calls. And there are roughly about 100 calls in there, and 70% of them are actually served from your cache. So today, the focus is going to be on EV Cache, which is a tier 0 microservice at Netflix. And what is EV Cache stand for, right? It stands for Ephemeral Volatile Cache. Volatile is a bit of a misnomer. I know the name was coined at least several years ago, but the cache is not volatile because it is indeed backed by SSD as well. And as I mentioned, there is a link towards the end of the talk which will go do a deep dive on EV Cache. But at high level, it's a distributed sharded key value store. It is based off of Memcached. It has in-region and global replication baked into the client itself. And we are going to spend a whole lot of time on global replication. It is built to withstand failures. When I refer to failures, I'm talking about instances going down. I'm talking about your availability zones going down, or your region itself going down. Also, the client is topology aware. When we say EV Cache, I would want us to think it is not just a microservice, but it is a combination of at least 5 different microservices, which are purpose-built for a specific operation. Like the global replication service is purpose-built for replicating the data. EV Cache client library is sort of at the heart of all these things, and we sort of rely or use the client library in a sort of a modularized fashion so that you can build like 5-6 microservices and use the underlying library. The server side is also linearly scalable. But when I say scalable, what I'm really referring to here is at Netflix, we also sort of see sudden spike in traffic, especially since we are almost Christmas is a few weeks away. Christmas is a very popular time, or New Year's is a very popular time where all the families get together. They want to watch their favorite Christmas movie. And we do expect a surge in traffic, and we sort of have to scale out our backend stateful services almost in a day's notice. Again, pre-scaling for a long period of time would cost us a lot of money, so we need to be able to scale up just with enough headroom, so that we are not spending too much money on the cloud cloud costs as well. At the same time, we are not running the risk of taking the service down. And this is a typical deployment of the caching solution itself. We maintain 3 copies per region, and we do that for availability reasons. And we also have applications deployed in 3 different availability zones within a region. Typically, reads always go to the local availability zone first, and if there is a cache miss, it gets retried in different zones. And this is the scale of the service that we're talking about. This is deployed in 4 AWS regions, spread across 200 clusters. When I'm referring to clusters, think of them as a set of, it is sort of helping or supporting a set of use cases or set of applications within Netflix's ecosystem. And we sort of maintain that level of isolation so that we don't run into noisy neighbor-related issues. And these 200-odd clusters are hosted on 22,000 EC2 instances. We do close to 30 million replication events per second and 400 million operations per second within the region. We store close to 2 trillion items on EV cache with 14.3 petabytes of data. With that, I'm going to let Shriram talk about global replication.
Awesome. Thanks, Prithvi. So this is Sriram Rangarajan. To be honest, this is my first conference talk, so super excited to be here. And thank you so much, AWS team, for giving us this opportunity. So let's get started. In the previous slide, we saw EV cache deployment in 1 region, whereas now let's expand that picture a bit of EV cache deployment in 4 different regions: US East 1, US East 2, EU West 1, and US West 2. Now, if you take a closer look into the slide, actually, replication happens in 2 places. 1 within the region and 1 across the region. Within the region is a quite simple problem. So it's being handled by the EV cache client itself. Whereas across the region is actually a stateless service. That's called the replication service. For the next 15 minutes, we'll be talking about this replication service. But let's take a step back. Before even understanding the detailed architecture and design of the replication service, like many of you are already wondering, hey, it's a cache data. Why do we need to even replicate the cache data? Why not just fetch the data from the DB and fill in the cache? If you're wondering that, perfectly normal, correct questions, but hold on your thoughts. We're going to talk about it. This is exactly the same slide what we saw previously. The homepage, the personalized homepage rendered by different machine learning algorithms, and 100 different microservices are called. And from these 100 microservices, almost 70% of the data actually comes from EV cache. Let's break down into 2 important things. 1, personalized homepage, and the other microservices. Let's talk about the microservices first. A very happy user coming to Netflix, logging into Netflix, say 100 different microservices are called. A region failover happens. What is region failover? The traffic from one region is evacuated to the other region. At Netflix, it's a very common practice that we do region failovers. Say, for simplicity and for discussion perspective, we can say that the traffic from US East 1 is rerouted to US East 2. Say replication has not happened. So now, since this user data is not available in US East 2, it's going to result in a cache miss. So what's the application team are going to do? They're going to fetch the data from the DB and fill in the cache. Perfectly normal. Again, cache is going to have a hit or a miss. That's a feature of a cache. So, but consider the scale here. Currently, we have roughly around 200 million users. Say 50 million users get served per region. So if these 50 million users are going to hit the DB, it's going to put too much pressure on the DB due to the thundering herd problem. How can we solve this problem? Super simple. Throw money at the problem. So just go pre-scale the database, and that way we have enough room for it. But what's the problem here? For example, for every region failover exercise, we need to go scale the databases. So just consider the amount of coordination that is required, amount of that cost that is going to happen by just pre-scaling this. So now, what is the end result of this? It's going to frustrate the user. So as we mentioned before, the goal of Netflix is to spread joy. So here the user is unhappy about it. So now let's consider a happy scenario, right? Replication has worked for some magic. So the data is already available in the cache. So now what is going to happen is that from the user perspective, he's not going to have any end-to-end latencies because the data is going to be readily available and the business is going to run as usual. So latency is an extremely critical factor for building this replication service. 2, personalized view. So personalized homepage powered by ML. It's a very, very, very common practice for some of the machine learning teams to use caching as a backend store. Oh, yes, you heard it right, actually, caching as a backend store. 2 reasons for it. 1, it's totally fine to have few cache misses because they can go and recompute the data for that user by either it's stored in S3 or Druid. Or the other reason is that if they wanted to store the same data in the database, it's going to be extremely expensive for them. So for some machine learning algorithms and for machine learning teams, caching is the persistent store. So now let's consider the same scenario. Happy user coming to Netflix, region failover happens, cache miss. So what is the team is going to do? Going to go and recompute the data and fill in the cache. Again, cache is going to have a hit or a miss. It's totally fine. But consider that for the scale of 50 million users, they have to go and recompute the data. These algorithms are extremely CPU intensive. So it's going to cost extremely high amount of money. Who's going to be unhappy? Netflix. So cost is another factor why we wanted this replication service was built. So the 2 factors what we saw from the technical aspects, the cost and the other latency. Now let's consider what is replication, right? So even if you take 2 steps back, it's like replication is nothing but a data movement problem. So we have roughly around 200 EV cache clusters, which is equal to 200 use cases. So now, from a platform team, we felt that if we own the data movement problem and the application teams focus on the business logic, it's like a shared responsibility to make the end user experience better. So that is another reason for building this replication service. What are the design goals of the replication service? Latency. As I mentioned previously, latency is a very critical factor for building this replication service. But we know that we don't want to promise false promises, so we cannot provide a sub-millisecond because we know that every replication is going to have a cross-region call. As well as we don't want to provide SLA in minutes or hours. Reason? It's a cache. It's going to have a TTL associated to it. So it's no point in even replicating the data at that point. So currently, we provide an SLA of 2 seconds. Tunables. As we mentioned previously, there are roughly around 200 EV cache clusters. Let's assume that these 200 is equal to the 200 use cases. We don't want to deploy different replication services for different use cases. Then it's very hard problem to, it becomes extremely hard to maintain the system. So we wanted one replication service to behave differently by just changing the configuration parameters. We have hundreds of configuration parameters in place, but one parameter, for example, is consistency. Say that if one app team wants, hey, I want the data to be replicated across the regions, whereas the other app team says, hey, I don't want the data to be replicated, but I want the data to be invalidated across the regions, just for consistency purposes. We have a property in place, or configurations in place. It's called the invalidate for set. If the invalidate set for set is set to true, we go and replicate sets as deletes, which makes sure that if the data is written in one region, we go and delete the other region just for consistency purposes. Whereas if it's set to false, we make sure that the sets are being replicated as sets. Extensibility. So again, the replication is a data movement problem. If we keep the same design and architecture, right, so then we can achieve different use cases. So in the later section, we are going to talk about how just keeping the same design and architecture, again, they have a slight changes in the design for sure, but changing some of the Kafka configuration, we can achieve different use cases. Example, caching is one example, how we replicate these cache events. The other example are write-ahead log, delay queues, but this is just a preview of it and more to come soon. What is the design requirement? As mentioned previously, we wanted the data to be available in the other regions. So high availability is always the P0 for us. And now many of you are already aware is that all these replications are all happening in parallel. So we don't have any notion of a last writer wins. So we cannot offer strong consistency. Currently, we offer best effort consistency. What is the best effort consistency here? As I discussed previously, if an app team says, hey, I want some sort of a consistency, just give me something, so we can go and set the property for invalidate for set, which makes sure that the data, if written in one region, we go and invalidate in the other regions. So high availability is P0, and consistency is P1. Currently, we offer best effort consistency. What are the design non-requirements? So as mentioned previously, we don't offer strong consistency. What does make is that we wanted to simplify this system design. We wanted to make sure we don't consider global locking, partial commit rollbacks, and transactional updates. Now, many of you are already aware here is that all these three factors are related to strong consistencies. Now, let's start understanding the workflow. Let's start seeing how the data from one region flows to the other region. Here, in this case, how the data flows from US East 1 to US East 2. What are some important components in this slide? Let's start with the EV Cache client. EV Cache client is a client library which is embedded in the app. It's actually responsible for two important functions. It sends a mutation to the local EV Cache servers, and it also initiates the replications. And it also initiates the replication by sending an event to Kafka. Replication service is actually broken into two important services. One, the reader service. The other is the writer service. What does the reader service do? The reader service actually pulls the messages from Kafka, then does sort of a business logic or transformations, and sends a cross-region call to the writer. The writer actually goes and writes to the destination EV Cache service. Let's start understanding the workflow. The EV Cache client sends a mutation to the EV Cache service. What is the mutation here? It can be an add, it can be a set, it can be a touch, it can be an increment, or it can be a delete. In parallel, it also sends a metadata to the Kafka. What is the metadata here? As we mentioned previously, EV Cache is a key value store. Other than the value, everything other than the value is a metadata. It can be a key, it is a TTL, it is a compression, on all the important related information. Why we don't send value to Kafka? Two reasons behind it. One, we don't want to put too much pressure on Kafka. We have seen use cases where the data can be a 4 KB, 4 MB, and also we have 40 MB. So if we send a 40 MB to Kafka, it's going to be too much pressure. So that is something we wanted to avoid. Two, for example, if two mutations happen within milliseconds, say T1, T2, say T1's data is already replaced by T2 data, then we don't want to even replicate the T1 data. So that is another reason why we don't want to send the value. Now the replications reader actually pulls the messages from Kafka and reads the recent value from the local EV Cache service. Now, it does some sort of a transformation and sends a cross-region call to the writer. The writer has a EV Cache client embedded on it. Now, it also sends the write to the destination EV Cache service. Now, when the app team goes and reads the data or reads the key, the data is readily available, and it's going to serve the data. We spoke about EV Cache client. We spoke about servers. We spoke about Kafka. We spoke about readers and writers. We didn't speak anything about SQS. Yes, we use SQS as a retry path. So whenever the failures can happen in path 4, the read path, the cross-region call path, or the write path, if any of these failures happen, the replication reader actually sends the event to the SQS. And we have a similar reader and writer for SQS, which actually pulls the messages from SQS, sends it to the writer SQS, and then sends it to the destination. Now let's take a closer look or detailed design of the readers and writers. Prithvi, please take it over.
Thanks, Shriram. All right, so what we started off was with a picture of deployment within a single region. Then we saw deployment with 4 regions. We saw replication service as just a black box. We are zooming in to the interactions or the data flow between 2 regions. Now let's try to understand the interactions between these components at a much closer look. Right? So on the left-hand side, what you're seeing is a Kafka cluster. And if you recollect from the earlier slides, we said we have 200 odd clusters. And to enable global replication, we could have taken the route of creating a dedicated Kafka cluster for each one of these EV cache clusters or the caching clusters, or have a single Kafka cluster that sort of tackles all the traffic from all these, right? So we went with the approach of just managing a single Kafka cluster. Otherwise, it is going to be a management overhead for the engineers who are looking into this service. And the way how we designed this is each topic sort of corresponds to the backend cluster, and the number of partitions is going to be a factor of the RPS that each of these clusters are receiving. So imagine a cluster just receiving 100 RPS, right? You don't need a lot of partitions for that topic. Whereas imagine a cluster receiving 1 million operations per second. You would definitely need a lot more concurrency and parallelism so that your Kafka consumers can consume them faster. The way how we designed this is each reader cluster is, from Kafka terminology, is nothing but a consumer group. So they are able to read the same set of mutations from the Kafka cluster. And the reader cluster is purpose-built to essentially consume this data from the Kafka cluster. And it is going to look at the payload and if it needs to apply any transformations. So for example, you want to, you got a mutation, but you want to invalidate data in all the other regions so that you want to keep the data consistent, right? All such transformations are going to be happening within the reader cluster, and the reader cluster will also do a read of the data from the local region itself. And a shrewd reader might look at this diagram and they'll be like, why do you need to read from 3 times, right? Aren't you adding read load on your EV cache servers? That's a fair point, but in practice, what we have noticed is like reads are extremely cheap operations, and they do not add a significant load on the system. So even though we are not sending the payload via Kafka cluster, we found that trade-off to be a very good one in our practice. And finally, we touched upon this, which is if any of these things fail, we do park all those failed mutations in SQS, and we have a finite amount of retries. We did not implement dead letter queue kind of a design because since it's a cache data, we can sort of tolerate some amount of mutations, lost mutations. We'll touch upon that in a second as well. We have seen the interactions between Kafka and reader. Let's understand the path between reader and writer closely as well. So on the right-hand side, you're seeing in US West 2, the writer cluster is present. Writer cluster is currently a REST server. We are in the process of rewriting it into gRPC server. All we do is send a REST call with the full payload. So I want to emphasize it's a full payload, and it's also bright red, so it is an expensive call. And then once the writer cluster receives this REST message, it is going to unwrap the message. It will see what kind of mutation we are talking about, and then it will issue the call to the destination cluster. And EV Cache client library is again embedded within the writer cluster. So we have made sure that there is like a lot of common code abstracted into libraries so that these services that we are looking at are just focused on what they're supposed to do and rely significantly on these common libraries. Extensibility. So if you looked at the overall design, a vast majority of the components are reusable. So think of RocksDB. RocksDB doesn't do any global replication. It's just node local storage, right? But you can apply the same design element and make your RocksDB globally replicated. Likewise, for folks who use Redis, Enterprise Redis does support, but if you're using stock Redis, it doesn't have any notion of global replication. So you can definitely use the same architectural paradigm to implement a generic replication service. Write-ahead log. So write-ahead log is something that all the databases have baked in. So whenever there are any, to ensure that the data is consistent, so that you can sort of replay the failed mutations. But imagine a situation where you have corrupted the data, right? Your DR strategy typically would be to take a snapshot and restore to a point in time where you know that the data is good. But what happens to all the mutations that happened after that snapshot? You need to sort of park those mutations somewhere. And we can use the similar architectural paradigm to build a write-ahead log as a service. outside of your database. And finally, delayed queues. So the solution or the architecture that we have described here, it does do 3 times of retries before giving up. But for a database workloads, you can't like never lose your mutations, right? You eventually want to make those requests succeed. So how do you handle that? You need to implement delayed queues. So if your downstream is down, like your database is down for an extended period of time, it is okay, but you need to still park that mutation somewhere and attempt to retry at a later time. And similarly, dead letter queue also falls into the same bucket. And we are investing into these based on some of the constructs that we have explained. And hopefully, if all of these things work out great, we would love to be back and share the results of these 3 services, which are going to follow a similar architectural paradigm. And in terms of extensibility, if you the core way how we are able to achieve all of this is due to Kafka. And I just want to share a few configurations. There are a few more, but the important ones are these. So in a caching use case, we really care about availability. And for availability, we really don't care about having quorum of a Kafka clusters when you're sending the mutations. It is okay if the leader is in an unclean state, or if the RF factor is not 3. And we don't need to have a quorum of replicas. We can have it at just 1. But for a write-ahead log, we really care about durability of our mutations. So we want Kafka configurations to be like a lot more stringent. It would definitely add additional latency, but again, you have to compromise on something to achieve the high durability. Again, these are just some of the extensibility things that the team is looking into, and we hope that we are going to achieve all of these things in the coming year. What are some of the design advantages? So in the context of the way how we have modularized, every component has a specific purpose. So if Kafka is bottlenecked on something, we can scale up Kafka cluster independently. If readers are blocked on something, bottlenecked on something, we can definitely scale it up. Similarly with writers. So all these are very much purpose-built, and they can be scaled up or scaled down independently. We also sort of have a predictable end-to-end latency because we sort of pretty much benchmark or like look at the amount of time that we spent between each of these stacks, from the time the mutation is sent from the client to the Kafka, from Kafka to the reader to the writer, and writer to the destination cluster. There are almost like five portions to it. And tunables, I think we already covered that, so I don't want to spend a lot of time on that. Cost efficient. Since we are using a single Kafka cluster to achieve all these mutations, we are not exploding the number of Kafka clusters. It is not a management overhead. There is a section dedicated for cost efficiency wins that we had. So I'll, again, do a deep dive on it in the later slides. Back pressure. Because we have so many moving parts, something can fail at some time. And we don't want one system or one component going down to bring down our entire system. So we have back pressure or throttling mechanisms baked in so that we degrade the performance, but we don't run into the risk of taking the system completely. What are some of the design pitfalls? Because the system that we are looking at is a stateless service, we can rely significantly on auto-scaling policies, but auto-scaling policies can be a double-edged sword for folks who have maintained Kafka clusters. If your consumer groups are constantly, there is a constant churn, you would see Kafka cluster is always in the state of rebalancing the partitions across the consumer groups, and it would attribute to all the increased or elevated latencies. So if you're going through this design, I would definitely watch out for setting the scaling policies on the right parameters, so that you're not always in this constant churn of scaling up and scaling down. You want to definitely aim for a smooth curve. Message duplication. So since when we do global replication, right, essentially you can rely on a client-driven architecture or a server-driven architecture. The architecture that we have we went ahead with is client side. Partly the reason is client is also doing in-region replication. That means every mutation also goes to 3 different copies within a region, and we need to pick a primary to replicate the data to the other regions. And we didn't want to introduce that additional level of complexity on the server side, so we decided, how about we just have a client library that does this additional job of sending this mutation to Kafka. But the design pitfall that I wanted to call out is whenever there are any library changes, right, you need to handhold some of your applications at times. And we had an issue where we were essentially migrating all of our Java apps. Netflix is a Java house. And we were migrating all the applications from Juice to Spring Boot. And due to the library changes, we noticed a pattern where we were replicating the same mutation multiple times. We have safety guards in place now. But I just want to call out with a client-driven architecture, that is a risk that you can run into. Cascading failures is again a side effect of not applying throttling or back pressure. Just wanted to make sure that I call that out. Observability. So observability is sort of eyes and ears to what is happening within a service. And as an engineer, I'm very passionate about observability, and Shriram is going to talk us through that.
Thank you so much. Observability and alerts. So I think one of the favorite topics of all the on-call engineers here. So without observability and alerts, just consider the life of an engineer, right? We don't know what the root cause of a problem is, or how can we even quickly understand what is the root cause of a problem. So we do have alerts and metrics at different places. We do have alerts at the SQS level. We do have alerts at the reader. We do have alerts at the writer. But due to this shortage of time, we have like 24 minutes left. So we wanted to emphasize on 2 important alerts, like the event failure alerts and the latency alert. And then also, we also wanted to emphasize on how auto-scaling is extremely crucial for maintaining such a distributed system service. And then, as we saw, double replication is one of the design pitfalls. So just getting into the details of how we even detect double replications. Let's start with a very, very happy path. So the graph, what you see on the left, is the events processed. What are events processed? The number of events that is read from Kafka are the events processed. We do roughly around 31 million replication events on an average. On a max, we do roughly around 40 million replication events. The write, which is the events failed, this is a very, very happy path. Like, we see a maximum of 40 failure. This is the data for the last 2 weeks. So as we saw before, all the events failed actually are retried by SQS. So again, here we do a retry of all the 30 failures, and wow, and 0% failure. This is the best time to be on call. Like, I want to be on call during this time. I think I was on call during this time as well, so I was lucky here. So again, but we are dealing with distributed systems here. So issues can happen anytime. It can happen due to a bug. It can happen due to a system failure. So let's start seeing more interesting things. Let's start with an on-call engineer. Let's start with a scenario where an on-call engineer gets alerted at 12:30 a.m., 1 a.m. in the morning. A CRR event failure. What is CRR? Is cross-region failure events. How we have configured this event? So for example, in the last 10 minutes, if the 5 minutes have more than 1,000 failure per minute, then we immediately go and alert the on-call. Why do we need to go and alert the on-call? Because high availability is the P0 for us, and we wanted to be very sure the data is going to be available in the other system, other regions. It's 12:30, 1 a.m. in the morning. What does a normal on-call engineer does? Watch Netflix. So what we do as here is that, like, the first thing what the on-call engineer does is that, hey, the CRR event failure, then we immediately see into the retry path. If there is retry path happening, then at least it's not a P0, because we know that the data is going to be available in the other region. We know that the data, but the latency is going to be on the higher end because there's going to be retries. It's not going to be within 2 seconds, but at least the data is going to be available in the region in seconds. What is a bigger failure? If even these failures happens, this means that the data is not going to be available in the other region. So this is a P0, and immediately the on-call immediately goes and understands what the actual issue is. This can happen due to 2 reasons. One, it can happen due to a bug. So bug is a quite simple problem. We go and roll back the build to a more stable state. So this will at least resolve the problem, and during the normal business hours, we go and understand what the reason behind is. System failures. It can be a memory alert. It can be a CPU alert. During that time, we throw more hardware at the problem to get at least the errors to 0, and then try to understand what the actual problem is. Next alert is the latency alert. Like a normal business hour, like we see this is the P99 latency. On an average, we see roughly around 2.0 seconds, and on max, we see, these are the set latencies, 2.14 seconds. Let's consider the same scenario, right? So a latency alert happening. On-call engineer immediately goes and sees the latency. And interesting that happens here is that only for one topic, so replication service is common across all the EV cache cluster, but seeing for only one topic, the latency is roughly around 500 seconds. Oh, this is one of the most important alerts or interesting alerts. The reason is that because it can be due to a bug, it can happen on the reader, it can happen on the writer, Kafka, SQS, network, combinations, permutations, everything. So almost like, or it can be a cascading failure as well. So we have a separate section where we go and understand or debug a latency. How do we resolve it? And how do we even deploy that to prod? That is have a later section, but this is again a preview of it. Auto-scaling. As we mentioned before, like for a replication service, we do roughly around 30 million replication on average. So, but as an EV cache team or a platform team, we don't want to go initiate a conversation to every individual app team for a special occasion so that we know that we are going to pre-scale our EV cache service. What can be the special occasions here? For example, live. As many of you already know that Netflix started live events. If the number of concurrent viewers goes high, the number of replication events also goes high. Holiday season. When the peak viewership goes high, for example, when Squid Game just released, the peak viewership went high, the number of replication events also goes high. A new service. It's extremely hard to predict the exact traffic of a new service, which wants replication. So it's very hard, we get the ballpark number, but with the ballpark number, we cannot go scale out EV cache service. Migration, testing. These are the few sample occasions, but what the main focus here is that we don't want to handhold the replication service, but we want the auto scale to happen automatically. This is an example. Say on October 31st, a new topic got added. And on the right, you see the number of instances also increased. If you see the pattern, like between the number of events and the number of instances, it exactly matches. So which means that the auto scaling was working perfectly. But for auto scaling to work perfectly, we need to have the right scaling policies as well. What are the policies we have for the replication service? First, CPU. So we wanted to be very sure that we use the maximum utilization of the resources. So currently we do a max of 70%. All our CPUs are working at 70%. But if the average goes beyond 70%, we go and auto scale the system. Network. This is a very important metric because as a platform team, we don't own the actual data. The actual data, as I mentioned before, can be a 4 KB, 4 MB, or 40 MB. Or if a new service all of a sudden comes and says, hey, I have introduced a new feature, let me increase the payload size from like 4 KB to 40 MB, then the auto scaling should happen automatically. So currently, if the network goes beyond 200 MB, we go and auto scale the system. Queue size. This is another important metric. The first two are the system. So one is the CPU and the network is, what is the queue size? This is an internal metric. As we saw from the design, the readers are responsible for reading the different partitions. And processing of all these partitions happens in a separate queue. And this is exactly the size of the queue is the queue size. So now where is the 700 number coming from? It's a magic number, to be honest. It's just based on experience. When we tried with a very low number, this auto scaling happens at a very rapid scale, which means that we are throwing more money at the problem without effectively utilizing the resources. Whereas in the case of a higher number, what happened with that is that some of the nodes went into a very unhealthy state because of memory issues. So 700 is based on experience, is based on the traffic pattern, but it's just by from the current production traffic. As mentioned before, auto scaling works perfectly if we make sure that the resources are utilized at the maximum possible. CPU. As I mentioned, we do a max CPU utilization of 70%. Currently, we have roughly around 2,000 instances per region, which includes both readers and writers. So consider that when 2 nodes goes down, do we need to alert the on-call? No. That which means that the on-call has to be alert almost the entire 24/7 for the entire period of 1 week. So what we do is that when an alert happens, if one or two nodes go down, we have auto remediations in place. We go try to terminate the node. If it's very less percentage, it's okay to go terminate the node, see if it goes the issue. Now comes the disk. Let's consider another scenario. Currently, we use a max of 40%, but an alert comes in, but a group of disk goes down. Now, we don't want to go terminate the nodes. What we do is that we go and alert the on-call. So the general theme what we have is that if couple of nodes or few nodes goes down, then we go and auto-terminate these instances. But if a group of nodes goes down, then we alert the on-call. Double replication. Like this is one of the design pitfalls of the current design, as client initiates the entire replication. In this graph, we see around 1.7 million duplicate events. From the same application, we have roughly around 1.7 duplicate events. As Prithvi mentioned, this can be a migration effort. I think around 2 years ago, we started an initiative of migrating most of our services from Juice to Spring. Juice actually uses an NF Kafka library, and Spring uses Spring Kafka library. Now, during this phase of a migration, if the client forgets to go and stop the replication, then the double replication will happen. What is the problem for this double replication? The data is going to be available, so that is no problem at all. But every replication event is going to result in a cross-region call that is going to increase the cost. So this is more of a cost optimization effort than actually a P0 or if the data availability problem. What can be the reasons behind the double replication? It can be a bug, it can be a configuration, or it can be a migration. How do we even detect these double replication? We use a very fancy way, the manual way. Because the problem is that the same, like for example, consider 1.7 million events, but the application is actually doing a 50% deployment in each. It's a perfectly valid scenario. Then this is not duplicate events, but these are actual events. So it's very, very hard to go and automate this process, but we are trying to automate it, but we don't want to generate a lot of false positives as well. Currently, what we do is that we do have a jobs in place, and the on-call engineer if the job fails for some reason, the on-call engineer goes and understands what is the failure is, goes to understand sees the metrics, sees the deployment model. If required, also goes and initiates with the conversation with the client's team. Let's talk about efficiency improvements. Like the last section on the double replication, we saw cost efficiency outside the replication service. But as Prithvi mentioned, this is the year of efficiency. We did a lot of improvements within the replication service, and I'll let Prithvi handle it.
Thank you, Shriram. So at Netflix, actually, we had a hack day where we invited all the engineers to come up with some crazy ideas. So we have done a lot of efficiency-related projects, but this is definitely going to focus just on what we did within the service that we're talking about. The first one is batch compression, and the second one is removing network load balancers. We did not talk about any network load balancers, right? So we'll see where it comes into the play. So we've been talking from the beginning that reader to writer is an expensive call because it's a cross-region call, and for whoever who looked at the AWS billing reports, the network costs come out as a bit of a sticker shock, right? That happened with us as well when we started auditing. And one idea that we had was all the data that is going from region A to region B for a particular use case. If you look at the data type, if let's say they're using protobufs or they're using JSON, a lot of fields are sort of common across a particular use case. We thought, how about we just batch these messages and then enable compression on top of this, right? And the results were quite impressive. And we did try out Z-Standard, Snappy, and gzip, even though we know that we're not going to be using gzip just as a data reference point. But eventually we settled on Z-Standard, the standard level compression. And what we noticed was the red line that you're seeing here is the average size of the data in uncompressed, which is 100, roughly hitting peaks of 100K. And the compressed data size was close to 70K. So we saw almost 35% in network bandwidth reduction. which resulted in definitely a lesser cloud bill cost for us. And this is sort of a breakdown of the previous slide, almost at a per use case level. The top line that you're seeing is probably one of our very high RPS cluster, which is called as pre-compute ranks. And the payload size is about 1.2 MB. And we could see that I've highlighted to the bottom. And after compression, it came down to roughly 400 kilobytes. So there is almost 65% compression savings for some of our largest clusters. So let's talk about network load balancers. Right? So between reader and writer, we were using network load balancers. Even now, we have network load balancers deployed in our architecture. But when we look at the cost, right, when you do a cross-region call, you're going to be billed at EC2 out cost and also for network balancers, network load balancers. And we had network load balancers for two primary reasons. One of them is the clusters are deployed in AWS accounts which are not peered, and we had to sort of rely on network load balancers to achieve the cross-region call. The second one was to have a predictable latencies and also obviously for load distribution. That's what NLBs are built for. But once we looked at the cost of this entire thing, we found it to be extremely expensive. So we thought, how about we evaluate it with a client-side load balancing algorithm and see how things look like and how the latency look like, right? So we eliminated network load balancers and tried to go direct EC2 from the reader to the writer instances. And this was the time when on April 13th this year, we migrated pretty much all the workload, which was roughly 50 gigabytes per second, handled by the NLBs, and all of them went pretty much to less than 500 MB. We still use NLBs as a fallback path, just in case our client-side load balancing fails on us. And for client-side load balancing, we use our internal DNS solution called as Eureka DNS. Now, all of this is great, right? Now, this sort of resulted in almost 50% reduction in the network transfer cost. Although you see a 90% drop in NLBs, that is what we were able to eliminate from the cost perspective, but we are still getting billed for the EC2 out costs. Did it really work, right? So the litmus test for us is to ensure that the end-to-end latencies remained under the 2-second SLAs that we promised to our service teams, and did the load balancing thing really work? So the right side top corner, the graph that you're looking at is the distribution of RPS that each of the writer nodes are receiving. And they are pretty much hugging to each other, which is a fantastic win for us. In the interest of time, I'm going to skim through very fast. So life of an EV cache engineer. So to give you a window into what we do, let me talk about the latency page. So whenever we get a latency page, this is at 10:20 a.m. In the morning, not too bad. It's not like we are waking up in the middle of the night. The usual suspects of a latency page are it could be due to your Kafka, and from Kafka, usually the offending ones are maybe the number of partitions that you have per topic is not high enough, or there is a significant consumer lag, or the join rate of the nodes in your consumer group is the churn is very high. On the reader side, you could be bottlenecked by your thread pools. So that was the queue size metric that we showed you earlier. And the writer side, it could be due to a slower backend itself. So it could be that your system has become slow because it's been up for so long. So these are the three places where we can see this issue. So once we got the page, we click on the page and we see, oh, there is a massive spike on October 14th at 10:20 a.m. Why did that happen, right? Let's skim through some metrics on the Kafka side. Oh, there is a significant spike in join latency. Why would that happen? Because there is a significant node churn. Is that true? That seems to be true, because around the same time, you see a huge spike in number of reader and writer nodes getting added by the auto-scaling policies. So once you peel the onions over and over, you can actually get to the root cause of the issue. So in this case, it happened to be one of those situations where one of the availability zones on AWS had a networking glitch momentarily, and we could have done better by retrying on a different TCP connection. But at that time, this incident has happened. We were not doing that, so that led to a bunch of TCP connections getting stuck in close-wait state as opposed to established state. And that led to a spike in TCP errors from both the reader side and writer side. So until we went ahead and did a redeploy, things got settled. This is again just a window into one of the incidents. Shriram is going to talk us through one other incident.
Thanks, Pratik. So what is the life of an engineer without issues? It's super boring. So an interesting engineer, like interesting issues makes the engineer life interesting as well as makes us better. So let's look into our next issue. So instance going out of discovery. So this is a spinnaker which we currently use for deployment. The green ones are the healthy nodes. The blue ones are the unhealthy nodes. If it unhealthy nodes, which means that it fails the health check, so it goes out of discovery. The gray ones are the ones which are auto-scaling. Either it is tearing down or new instances coming up. So currently we can see that almost 50% of the instances are in unhealthy state. What an on-call engineer does? Immediately goes and does an SSH into that and usual suspect, the heap issue. Now understanding the memory utilization of the node, we see that around 1220, the memory utilization almost went from 2 GB to 10 GB. Why can this happen? Two things. The reason is that it can be an increase in traffic or it can be an increase in the payload. Now by closer looking and taking the heap dump, we saw that, like as I mentioned previously, every reader is responsible for reading multiple partitions and each partition is being maintained in a queue. So these queues were unbounded and there were roughly around 700K items in the queue and each item was only a few KBs, but the entire queue size was roughly around 1.3 GB. So since there are multiple queues, so the instances went out of memory. What is the cause? What actually resulted by this issue? So since the reader is responsible for multiple partitions, so some of the topic which even didn't have any changes in the traffic or changes was getting affected. So you can see a latency spike for multiple topics here. What is the solution for this problem? Apply the black pressure. So the problem was pretty complex, but the solution here is that we updated a data structure from an unbounded queue to a bounded queue. Great, we saw the problem, we saw the debugging process, and we saw the solutions. But how do we make sure that the solution is working perfectly? Earlier, I had an opportunity to work in a startup where we had an amazing fancy testing way, testing it in production. So what we do is that if we have an issue, we just take the problem, fix the code, deploy it in prod. If there's an issue, okay, we go retry the issue again. If if the solution works, amazing, we go to the next issue. But we are at Netflix, and this is the tier 0, and the scale we are working at, we don't have the luxury to test it in prod. But the current way, right, but the current design allows us to do the entire testing without 0 code changes. How? Just add a new consumer group. We know from the issue that what are the topics that got affected. Just rerouted these topics to the new consumer group, and with all the tunables in place, just reroute the traffic to a test writer and then to a test EV cache cluster. That way, we can actually test the data, live data in a live environment without actually affecting the production traffic. So what this gives us? It gives us the confidence. So for example, memory issues are extremely complex problems. We need the traffic pattern, but we also need the confidence that our fix is working fine. So this system design helps us to do that. Future. We have work cut out for the next few years. So what are the things we are looking at? Currently, the entire replication service is in IPv4. We wanted to migrate it to IPv6. So both readers and writers are currently running in EC2 instances. We wanted to do container migration. Generic service. As we mentioned before, it's a data movement problem. We wanted to achieve different use cases by this service. So we are working on write-ahead logs, delayed queues. If it all works perfectly, we'll see you again in 2024. Thank you so much, and thank you so much for your time, and have a great rest of the day.